for steering purposes. So you see the weld right here, and these welds typically are made on relatively high strength steel. You're talking about, if you remember from yesterday, we had these grades. From 36 was the base to 50, 42, 50. This is around 60 or 65 KSI yield. So what happens during welding is, if it's not done properly, you can have some quenching and hardening of the base metal next to it. So as part of quality control, they will take pieces, full A-arms, assemblies, cut them up, and look for the hardness in that region right next to the weld to make sure the process doesn't make the material too brittle, too hard for ductility. And then they will also apply these criteria about, getting a good fusion here, getting fusion through the depth, but not. One of the issues when you're dealing with thin tubing is you don't want to melt through. So it's a very delicate balance between having fusion, but not too much, not melting through. We talked about how they do the fasteners. They do a lot of durability testing and pieces that they just pick out of the factory, and they go and they ride it for thousands of hours. So it's a type of industry where they don't consider testing all that expensive, because that A-arm itself is, as a standalone piece, not worth a whole lot. It's just a little bit of metal that was put together with welding machines. So it's okay to take it out of production and do the necessary testing to make sure everything is still going the way it was going last month when they did, the prototypes and all of that. So there's a lot of quality control in welding of these components. It's the same for automotive. There's no change. I'm going to switch gears a little bit and talk about pipelines and everything that falls under what we call the American Petroleum Institute. The American Petroleum Institute has specifications. It also has recommended practices, and then therefore it becomes somebody else's decision as to whether these practices have to be completed on a specific project. And sometimes the government makes that ruling. So this is tying back to the material aspect we were talking last time. So this is a very, very general section of the spec, just talking about mandrel tubing and casing hangers. I picked that just as an example to show you have to meet tensile requirement, hardness requirement, and impact. Why would I care about impact? Well, if I'm in the North Sea or somewhere where it's cold weather, I want to make sure the steel doesn't become brittle at low temperature. So this is something, if I start applying a certain criteria, now all of a sudden I have additional testing requirements. Most ASTMs don't have impact requirements as the basis. It's a supplementary requirement, or you have to go to a special grade of steel that is specially designed for cold weather. So I'm pointing it out because we were going through API. What I wanted to do is show you how they will deal sometime with welding inspection. This section here, if it's a pressure containing weld, 100%. So this is an additional requirement to the welding procedure, the qualification of the welder. No matter how you do it, and API will tell you some of that as well. It's not just the American Welding Society. But what API tells you in this general paragraph is, whatever you weld, I want it to be fully inspected using non-destructive testing. So that is more than just visual. You have to come with probes. They have radiographic. You take an X-ray. That's pretty complicated. You have to do different angles, looks for cracks. Ultrasonic methods, it's very user sensitive. Essentially, you come with a probe. So if this is, say I'm doing a groove weld, because that's where it's done a lot. So this was my prep on a groove weld right here. And I came on and just did a lot of welding. This is a big plate. or a big pipe. Oh. Okay, now I come with a probe that I put on the surface, send a wave at 45 degrees, it comes back, goes through the well. If there's any interface in the well, it will come back at a specific wavelength or a time lapse here, tell me I got an indication. And you can do this by scanning and actually get an image, or you have to do it in a trained way where you move your probe and try to see if the same anomaly persists from one position to the other, because there's some minimum size requirements. Below a certain size, you're okay. You say, oh, well, I got a little porosity in there, or I got a little slag that wasn't taken off. But you have very specific requirements. And that's the interesting thing. They're not listed in this section. So if we wanted to know, okay, so I got to do ultrasonic testing. Now, how do I need to do it? Now, you go into API, into other sections, they will tell you how to do the inspection and what is the acceptance criteria. So this is essentially an example where you don't have a choice to do more than the basic quality control. Yes?
Is this true of pressure containing wells, or for example vacuum, which is regular wells, do they not need as much inspection or as much care?
I don't know that there's a whole lot of vacuum system with API. Most of the time it's for transportation of either crude oil, natural gas, and it will be pressurized. So essentially each time you put together a pipeline, you have to do a lot of non-destructive testing after you're done welding.
The reason I ask is because like MIT machine, if you ask them to weld for you, they'll ask you first off, is it pressure welding? If you say yes, they'll be like, we won't do it.
Yeah.
Vacuum welding or other kind of welding, they'll be like, oh yeah, sure, we can do that. So
I don't know if what they mean by vacuum. You can ask them if it just means it's not regulated. Because I think that may just be the case. If I was putting together a high quality vacuum system, I would also want to have specifications for quality. But probably what they mean is there's no imminent risk. All you can do is contaminate your experiment. so they're willing to do it. If it happened that you could lose escape chemicals, you shouldn't have them do it, because what they're telling you is they don't do high quality. They don't have the procedures to go back. They don't have ultrasonic testing methods to go back and learn from mistakes, because on large projects, what happens, even the good welders, the ultrasonic test guy comes back, start putting some red paint on the welds. He's starting to figure out what he did wrong, because he's got a lot more to do. And it's really nice to have them come the first day, to have the inspector be there, so it's not all the project is done and then now they have to redo all these connections because they were not, using the proper procedure, didn't get full fusion. Yes, that was a good question. Okay, very briefly on aerospace components, I mentioned at the very beginning of the class, we need reliability. This is not an option. It's not a question whether we get a little leak and now you have to dig up the soil, clean it up. This is very serious when you have a fuselage up in the air. I'll talk a little bit about solid rivets. There are a lot of rivets and fasteners. It's a whole world. If you're interested to build something quick, I encourage you to go to a catalog and see all sorts of things you can do. But in this class, I'm going to try to tie it up with some of the things that were discussed by Professor Eker and myself, and maybe Mike Montfort. So we're dealing here with aluminum. So you can have a counter set type here where once you put the paint on the fuselage on the outside, you don't have bumps. And that's good for reducing the air friction. You come with a variety of tools to hold the head on one side and smush the bottom here. So in the end, you have a rivet that's just going to be somewhere like this, almost square, depending on your design. And that's holding two pieces together. So I've got one plate here, another plate. Now, that's a lot of plastic deformation to go from something that is just a cylinder to something that's flattened up. And depending on the grade of the aluminum, and how it's being pre-processed, you do it in one or multiple operations. You try not to have too much hardening in the aluminum. The more hardening you have, the higher are going to be your residual stresses here. So what I did, I was an undergraduate back then, and in quality control, I would go to the guy in the, at the furnaces. What he was doing essentially was the heating it to solution. So if you remember a little bit, the aluminum phase diagram, say if it's with copper. So I got copper here, and I got aluminum. This is a phase diagram. We're looking at different composition. So going that way, there's more and more copper. So a lot of time you get the alloy here at high temperature as a single phase. Say we call it alpha, FCC of a certain parameter. So you get it up there and you quench it really fast. I think the rivets, we were quenching them in the water because it wasn't all that hard. It wasn't that hot. It wasn't creating a lot of residual stresses. These were already formed. They already had the head part. It looked exactly like these. So they were in little baskets. You throw them for this high temperature. It's talking maybe 400 degrees centigrade, maybe more or less. Cool it down. And what was happening with a lot of these rivets, as soon as they came out the bath, sometimes it was a salt bath, sometimes as soon as they cool, we were putting them in a freezer to prevent the aging from taking place. And they had to be taken out of the freezer, installed, I believe, within half an hour. And what happens when you install, when you go to the process of making that deformation, you actually activate the aging process because you got all these dislocations, all the internal material components moving and helping form these little precipitates that hardens your material. So it was kind of a win and win. You wait until you're ready to complete your joint. And as you complete the joint, you start forming the precipitate. And then just at that ambient temperature, it will age to at least 50% higher yield strength than what you started with. To me, it was impressive. Now, when I was talking to this in terms of quality control, you cannot imagine how many rivets we were pushing. And in the same way, after 45 minutes, after all sorts of conditions, slightly higher temperature, it was just to make sure that when it's done in fabrication, it won't be a problem. So we were constantly verifying our margins of safety for the installation of those rivets. So they wouldn't start cracking if the guy waited an extra 5 minutes, and now it's been 35 minutes, it's already started to harden after coming out of the freezer. So it's essentially quality control, but on the procedure. And that's what is very unique about aerospace. They do a lot of that. They will have logs to make sure the oven was at the right temperature. They'll have a little junior guy taking notes of everything, and then that's how they know if they ever come to a problem. They need also to be able to explain it. Oh, yes, that bag was mislabeled. It stayed 45 minutes. These rivets were installed over there. We're drilling them all out, starting over again. So it's a very, very expedited process, and it's very documented as opposed to other industries. So I hope I showed you a little bit of the spectrum. And I did have a few closing notes here. So in terms of using materials, we're halfway through that module. I want you to think about what are the requirements. What do I need for my prototype? What is acceptable and not acceptable? We talked about that mostly through example. Then you have to say what you want. And that, I think, I helped you a little bit when I start showing you all these standard specification, the STMs and everything that's out there to help you do that step. Then there's the system aspect. And we talked about that a little bit, how everything's going to be joined. Are we going to do a full system testing? And this is where reliability, durability starts coming into play as opposed to the individual components. When I said about what you want here, what I'm thinking is the material, the process, and then quality. So the next lecture is not going to be tomorrow. Tomorrow, Professor Eager will take over and continue on the welding. Next week, we're going to continue on more on what you want. But not in terms of standards, more in terms of the application, so more from an engineering standpoint. Everything so far has been more, okay, these are the procedures, these are things that can help you. So I'm going to talk about demand, factor of safety, and how you start putting things together. Thank you.